Hi there, my name is Rita Sigby, and I created an artificial pancreas model to optimize insulin dosage. Here's my table of contents, and here's my abstract. Here's my background. Diabetes is a serious disease that affects more than 537 million adults, and is increasing at a rate of 7.3% annually, and in 2021 alone, it caused the deaths of 6.7 million people and $966 billion. Diabetes can be managed, though, by controlling the 4 pillars: diet, exercise, medicine, and blood glucose measurement. Insulin regulates glucose levels in blood, and autocorrecting insulin pumps are called artificial pancreas. They can be used for type 1 and type 2 diabetes. Current insulin dosage is only based on diet and specifically total carbohydrates. Current research suggests that mealtime insulin doses of treatment in people with diabetes should also take into account pre-meal hypoglycemia and the size and composition of meals. New research suggests that fibers are not digested and do not contribute to blood glucose levels, and they take carbohydrates out of the body before they break down into glucose. Insulin is not only expensive, but the major cause of hypo and hyperglycemia if not calculated and dosed correctly. But a continuous blood glucose monitor, or CGM, has the ability to take blood glucose readings every 15 minutes or on demand. However, by itself, the CGM has helped out but hasn't eliminated the conditions of hypo and hyperglycemia. The insulin dosage needs to be correct to prevent these situations. This feature only deals with carbohydrates in the meals, but it does not address insulin requirement for high blood glucose level. Based on this, my research problem is it possible to create an artificial pancreas model to investigate the blood chemistry and to determine if the current insulin dosage models are valid? Here's my hypothesis. An artificial pancreas prototype is constructed, and which will respond to changes in blood chemistry. Net carbs are a better measurement of insulin dosage rather than total carbs. The prediction of the total amount of chemicals needed would actually fall into zone A of the Clark error grid. And current insulin dose calculations can be modified to present the overdose or underdose of insulin. Here's my materials that I use for this project. Here's my procedure. I first assembled a circuit to look like an insulin pump. Then I created a solution of 7.1 grams baking soda and 500 ml of distilled water. I calibrated a circuit so the pump stops, the pH is neutralized. Then I used 100 ml of my solution and 100 ml of vinegar, and then I measured how it would take for the pH to stabilize. I repeated the following experiment with the following variations. I examined the insulin dosage formula to see how it can be modified based on the results above. Here's the chemistry. Based on all of this, the ml of vinegar needed for this would be 14.62 milliliters. Here's my artificial pancreas versus my current project. This is the human body in this project. Blood glucose level, high pH solution, blood glucose monitor affects a high level, the conductivity, detects the basicity, the insulin pump runs and the pump runs, the insulin is pumped into the bloodstream and the vinegar is pumped into the basic solution. Loose roller turns to normal, basic solution is neutralized, the pump stops, and the pump stops. Here's what the connected circuit look like. These are the potentiometers. The potentiometers are basically the heart of the circuit board. The potentiometers, as you see, these white knobs here are turned specifically in these 3 directions. As when you do so, the solution, once the solution is neutralized, the pump will stop due to these. Here's what my baking soda solution looked like. The reason why it's blue is because of Brothwell blue solution. Here's my vinegar solution look like, and here's what my neutral solution look like. This is the conductivity sensor. If these little metal pieces right here get the solution on them, the pump will completely stop working. Here's the motor and alligator wires. Here's the motor, here's the alligator wires. And here's table 1, endpoints for artificial pancreas. Here are all the runs, percentage error, minimum and maximum standard deviation, and it falls into zone A of the Clark error grid. You might be thinking, what is a Clark error grid? This is what a Clark error grid is. This is a Clark error grid, and they are usually used for diabetes, like blood glucose calculations. Zone A is the most accurate, and Zone E is the least accurate. So you do want your results in Zone A, unlike Zone E. Here are the chemicals needed with mixing. The reason why I'm doing with mixing, and on the next slide, without mixing, is because they're simple and complex carbohydrates. These play a big role in insulin in this project. So simple carbohydrates are digested much faster than complex carbohydrates. So you take insulin for your simple carbohydrates, and then once once your pH goes extremely low, you get hypoglycemia. And then to fix this, you may take sugar to raise your blood glucose. But then at the same time, the complex carbohydrates are digested, and then you go into hyperglycemia. You take more insulin to lower this, and it is a never-ending cycle. Here's the chemicals needed with insoluble fiber. The reason why I'm using insoluble fiber in this project is because, and also this also ties into then use net carbs instead of total carbs, is because insoluble fiber is counted in total carbs, but insoluble fiber isn't digested and doesn't contribute to blood glucose. So you're incorrectly measuring. But if you use net carbs without the insoluble fiber, you are using the correct measurement of carbs because you are not including things that aren't counting towards the blood glucose. And here's the vinegar needed with insoluble fiber. Here's a summary of all the tables, 1 through 5. After this, the percent reduction due to fiber is 9.46%. The reduction in fiber due to pH is 4.34%, and the reduction due to no mixing is 1.89%. Here's my insulin equation and modification. So the current insulin, this is the current insulin equation, but since I'm using net carbs instead of total carbs, carbohydrates, the insulin dose, and the total grams of carbohydrate in a meal divided by the carbohydrates divided by 1 unit of insulin, which is usually 10. The average mealtime total carbs in a day, 200 grams per day, and the ADA, which is this American Diabetes Association fiber recommended in a day is 40 grams, so the current insulin dose is 20 units, but my modified insulin dose using net carbs is 16 units. So if projected reduction is 20%, you need 20% less insulin than normal. And the response changes during the day and will depend on the insulin resistance in the body during that time. Insulin resistance is how your body reacts to insulin during the day. You could have high insulin resistance in the morning, but not so high in the afternoon. Here's the total blood glucose ranges. The amount of blood in a person, liters, the amount of glucose level, the total amount of blood sugar in blood, and the total amount of blood sugar range in grams. The low end is 3 grams, low end here is 3 grams, and the high end is 13 grams. This may not seem like a lot, but only one serving of ketchup has more blood glucose than the low end of the blood glucose range in grams. Here's the percentual sources of error in my project. The stirred solutions. There could have been some baking soda that didn't get mixed in, so it doesn't add up when I stirred the solutions. There wasn't a way to tell if all 3 potentiometers stop at neutral. The 3 pH of the distilled water wasn't always 6.4, which is a neutral pH, so there could have been some measurement issues. There may have been imprecision when measuring baking soda out, and when adding the vinegar to the baking soda, some of the solution may have overturned, resulting in fallacy. In place of glass containers, this project used plastic, which may have somewhat skewed the results. Here's my conclusion. An artificial pancreas prototype was assembled, which responded to the changes in blood chemistry. Net carbs were a more precise measurement of insulin dosage in comparison to total carbs. The prediction of the actual amount of chemicals fell in Zone A of the Clark error grid. The current insulin dosage calculations were modified to present overdose or underdose of insulin. And when using the pump after solutions are neutralized and added excess vinegar, the pH was acidic and the pump started again to get back to its neutral pH. This shows that my model of an artificial pancreas did work like an actual artificial pancreas in real life. Future work. In the future, this project could be expanded by using it to model different delivery of different medicine, taking into account other variables such as exercise and diet, investigating the difference between type 1 and type 2 diabetes and its impact, beginning more looking at actual artificial pancreas, as this project is on a basic standard by using baking soda and vinegar, and looking at the difference between different types of insulin dosages, basal and bolus, when combined with a diet and exercise. Here's my bibliography. Thank you for your time.